So, let's talk about math. More specifically, let's talk about math in computers and software. You may have heard before that all computers know are ones and zeros. This statement is true as far as binary computers are concerned, though concepts such as ternary computers allow for 3 values instead of 2, and I'm not even going to get started on quantum computing. For the purpose of this video, we'll be looking at binary computers, and we're not going to go too deep into things. Let's take a look at those ones and zeros we mentioned before. Those ones and zeros are what are known as bits. A bit can either be on or off, which represents their two possible states. On a computer, these bits will then be organized into bytes. How many bits a byte contains is dependent on the hardware, but most modern systems have standardized on 8 bits per byte. Now, looking at a byte which contains 8 bits, there are a maximum number of unique combinations of different bit values. This can be calculated as 2 to the power of 8, which equals 256. A much larger number of values can be obtained by combining 2 bytes instead of 1. In this case, 2 bytes, this is 2 to the power of 16, which equals 65,536. In the software, a single byte or a group of bytes can be used to represent a number, a string of characters, contain a memory address, or possibly many other things. However, your computer and its CPU aren't going to give a damn what these bytes represent. They're all just contextless ones and zeros to execute instructions on. The program you write will provide context and tell the computer what instructions to perform and on what they perform them on. The language you write the program in will abstract this into something easier for a human to understand. For simplicity's sake, I'll be using C as a reference. In C, you have a number of different data types which represent different combinations of bytes. These data types are also used to contextualize how these bytes are expected to be used. For example, you have the char data type, which represents a single byte, or the int data type, which usually represents 2 or 4 bytes of data. A char is typically used to represent either a very small number or a letter, whereas the int just represents a number. The exact definition of some data types is dependent on the CPU's instruction set as well as the compiler you are using. Regarding data types, integer types, those that only store whole numbers, usually come in signed and unsigned variants. Let's take a look at a short data type as an example. An unsigned short, which contains 2 bytes and thus has 65,536 unique possible combinations, has a value range of 0 to 65,535. A signed short, on the other hand, takes a single bit and uses it to indicate whether the number is negative or not. In this case, the value is minus 32,769 to 32,767. Beyond the integer types, we also have floating point types, which contain fractional numbers with decimal places. These are the float, double, and long double data types containing 4, 8, and 10 bytes respectively with a precision of 6, 15, and 19 decimal places. Continuing the use of C as a reference, the language provides you with a number of arithmetic operators you can use on the data types. These are fairly standard: addition, subtraction, multiplication, and division. Beyond that, you also get the modulo operator, as well as an increment and decrement operator. Addition, subtraction, multiplication, and division all work about as you expect them to. The modulo operator allows you to get the remainder after division, and the increment and decrement operators allow you to increase or decrease a value by 1. This might seem all simple, but unfortunately the resulting values of some of these operations might not be what you expect. Let's take a look at the classic strategy game, Civilization. For those unaware, in one particular iteration of Civilization, Gandhi had a reputation for being a Nukapi fiend. The explanation given for this observed behavior was simple. In Civilization, leaders have predetermined stats scaled from 1 to 10, and as a result, the developers ended up storing these values as unsigned chars with a value range of 0 to 255. This is reasonable. Gandhi, by default, had a very low value for aggression. As the game went on, Gandhi would reportedly develop certain civics that would augment his aggression values. On one of these, would subtract from its overall aggressiveness. Now, normally if you subtracted, say, 2 from 1, you would expect the value to be -1. If you recall, an unsigned char has a value range of 0 to 255, so -1 isn't the possible value in this case. You might think that the value would simply clamp to 0, but this isn't the case either. The truth is much more frightening. Instead of ending up as a 0, Gandhi's aggression value ended up overflowing, leaving him with an absolutely furious aggression of 255 out of 10. Values overflowing like this will occur with basically any data type or value you define if given the chance. The Y2K problem, which an enormous amount of money was spent to fix, was due to early programmers representing years with a mere 2 digits, and in the future we'll be looking forward to the same thing with the year 2038 problem. As highlighted by Civilization, how each data type behaves might not be what you expect. Each has limitations in how large or small of numbers it can hold, as well as limitations on the data they may represent. Let's take the integer types as an example. They only represent whole numbers without fractions. If you have 2 integers, such as 3 and 3, dividing 3 by 3 yields 1. Dividing 3 by 2 also yields 1. The aforementioned modulo operator is useful in such cases as it'll let you know the remainder. In the case of 11 divided by 3, the result is 3, and 11 by 3 has a remainder of 2. Now, floating point numbers aren't without their issues either. Let's take a slightly deeper look at the float data type. Under the hood, a single bit is used as a sign, 8 bits are used to represent an exponent, and a further 23 bits are used to represent a fraction. This looks good and all, but unfortunately the simple fact is that floating point numbers cannot be entirely accurately represented in a binary format. Larger data types such as the double and long double can get you better precision, but there are still limits on how large a value can be stored and to what precision that is. What you get as a result of issues with floating point numbers are called rounding errors. These errors have been responsible for a number of issues in the past. On that note, let's take a moment to talk about the MIM-104 Patriot, also known as the Patriot Missile Long-Range Air Defense System. Though the issue has since been fixed, the Patriot missile system had a particular software bug that resulted in tragedy. On February 25, 1991, an Iraqi Scud missile hit the barracks in Dhahran, Saudi Arabia, killing 28 soldiers from the U.S. Army's 14th Quartermaster Detachment. The Patriot was designed such that when it detects an incoming missile, it attempts to detect the incoming missile a second time in order to avoid false alarms. Unfortunately, the system had a bug related to timekeeping that prevented the second detection from taking place. The error was caused by an inaccurate calculation of the time since boot. The time, in tenths of a second, was measured by the system's internal clock and multiplied by 1/10 to produce the time in seconds. This calculation was performed using a 24-bit fixed point register. Unfortunately, the use of this register as part of the calculation resulted in the time being incorrectly rounded as a portion of the fraction was truncated. This rounding resulted in the system time slowly drifting over the course of many hours. After 100 hours of operation, the slight error introduced on the calculations was magnified to around 1/3 of a second. A Scud missile, which travels around 1600 meters per second, was able to travel more than half a kilometer in this time, far enough that the Patriot was unable to locate it on the second detection as it wasn't looking at the right place in the sky. As shown in the example of the Patriot missile system, the use of floating point numbers can be dangerous if mishandled, and small inaccuracies can build up over time. This is not to say that they should be avoided, but one should take care when architecting a program. Slight inaccuracies are often not an issue, and you often only need an approximation of the number in the first place. In many cases, a bug in how you handle arithmetic might have next to no consequences. On the other hand, software and systems designed for serious applications, anything that might change someone's life, such as financial or medical purposes, should be treated with absolute care. Have a nice day, and see you next time.